All right, we've mentioned colligative properties in the last podcast, and I want to talk about them more formally. So, there are certain physical properties that will change when you have a more concentrated uh, solute in the system. So the four properties that will change are the boiling point, the freezing point, the vapor pressure, and the osmotic pressure. The boiling point will increase as I add more particles. The freezing point will decrease as I add more particles. The vapor pressure will decrease as I add more particles. The osmotic pressure will increase as I add more particles. Two of these colligative properties are intimately linked. That's the boiling point and the vapor pressure. So let's talk about these two physical properties conceptually, and then we'll go into how adding more particles change these physical parameters, and then we'll talk about some mathematical relationships that we'll want to know for the exam. So let's do what Albert Einstein used to call a Gedanken or thinking experiment. Let's have a beaker of water. So this is simply distilled water. And I'm going to take a larger beaker and I'm going to turn it upside down to create a closed system. There are water molecules at the very interface of liquid and gas that have just enough kinetic energy to go from liquid and gas. So there are certain water molecules that have enough kinetic energy to undergo a liquid to vapor phase transition. Of course, this is called evaporation. So we have liquid water molecules that become gas water molecules. And when they're gas water molecules, they're going to have very little IMF. Remember, intermolecular forces will decrease as we go from solid to liquid to gas. The delta S increases as I go from solid to liquid to gas. The delta H increases as I go from solid to liquid to gas. And the best explanation for this is that the heat is actually breaking the IMF, and the molecules with less IMF have more freedom to assume random orientations in space. We know gas molecules can freely vibrate, rotate, and translate. And so these molecules will bebop around. Some of them may collide with the interior surface of the beaker that's inverted. And as soon as they collide, they will condense. This condensation, via the influence of gravity, will result in a ring of water molecules formed at the bottom of the beaker. This is why Mama gets upset if you put a cold can of Coke on the table without a coaster. This condensation will result in deformation of that beautiful antique table that she has in the dining area. Also, we can recollide with the water interface. This is going to continue. Now, when this begins, the rate of evaporation is greater than the rate of condensation. But eventually, these two rates will equal each other, and we will have a phase equilibrium. That means once we are at the phase equilibrium, the rate of evaporation is equal to the rate of condensation. So every time a water molecule goes from liquid to gas, there is a concomitant gas water molecule that goes from gas to liquid. At this point, the pressure that the gas phase exerts on the liquid phase is called the equilibrium vapor pressure. Now let's look at a situation where we have solute that's dissolved in the beaker of water. So I have water, but let's say we have NaCl. Na plus, of course they're smaller. Cl minus, of course they're larger. And for both Na plus and Cl minus, we have water molecules that surround these ions. And I'm just going to illustrate this in a cartoonish fashion. And then off to the side, I'm going to show more detail. So when you dissolve an ionic salt in a solvent like water, you don't have NaCl. You have solvated Na plus, you have solvated Cl minus. And all of these ions, if you have a homogeneous solution, that is, you cannot detect solid, all you see is a clear solution. This is what is happening on the molecular level. Now, let's show a little bit more detail. I have an Na plus. Of course, this is sodium. And I'm going to have water molecules that surround Na plus, but it's going to be the oxygen atom that surrounds the Na plus, because I have a partial negative charge on the oxygen atom and an integer positive charge on the Na plus ion. And we know from really the first scientific law we ever learned is that opposite electrical charges are attractive electrical charges. And so we have a series of intermolecular forces when we have a solute that's in our beaker of water. Now, let's also look at Cl minus. Water still surrounds Cl minus, but its orientation is completely different. Now it's the partially positively charged hydrogen atoms that surround the Cl minus. And these ion dipoles, they're really significant because they occur in large populations. And so you're going to have, again, an array of IMF, The orientation, again, of the water molecule is very different, because it is the partial positively charged hydrogen atoms that interact with the negatively charged chloride ion. Whereas with sodium, it's the partially negatively charged oxygen atoms that interact with the integer positively charged sodium cation. When water solvates these ions, it has to sacrifice kinetic energy. So in other words, I have to input more energy to break these IMFs for water to go from the liquid phase to the gas phase. So number one, not as many water particles are in the gas phase when we reach this evaporation condensation equilibrium. There are going to be less H2O molecules in the vapor phase. In other words, adding solute lowers the vapor pressure. Now, this point is really critical. Most students do not fully grasp the proper meaning of boiling point. The boiling point of a compound is the temperature at which the vapor pressure is equal to the external pressure. Because adding solute lowers the vapor pressure, I must input more heat energy to break these IMFs so that more water molecules are in the vapor phase at equilibrium. Said another way, when I lower the vapor pressure, there is a concomitant increasing of the boiling point. They are intrinsically linked to one another. So if we go back to the beginning of this lecture, notice that boiling point goes up when vapor pressure goes down. Now, one last thing I did not mention about vapor pressure that is important is vapor pressure is dependent on intermolecular forces. Since increasing temperature will break intermolecular forces, vapor pressure increases when temperature increases. Vapor pressure decreases when IMF increases. Adding a solute to a solvent increases IMF, which decreases vapor pressure, which increases boiling point. Now let's talk about freezing point. When a solvent begins to freeze, it's important to understand that this freezing occurs when a lattice, and this lattice is a three-dimensional array of crystals, begins to form. When I add solute to a solvent, the solutes, because they're again interacting with the solvent with IMF, so I'm going to show the solute as X, the solvent as a dot. I'm not able to have any kind of organized structural relationship between the dots because of the presence of my X's. This lowers the freezing point. The molecules actually have to begin to slow down such that solvent molecules begin to gravitate to one another and build this lattice such that we can have a phase transition from liquid to solid. So this is the conceptual explanation of how adding a solute lowers the freezing point. Finally, let's talk about osmotic pressure. Let's say I have a U-tube, not the kind of U-tube you're watching, but an actual tube, both ends of which are open to the atmosphere. And we have a semi-permeable divider between what we call side A and what we call side B. Now let's say that A is 100% H2O, doubly deionized distilled water. And on the right side, let's say we have a 20% solution of NaCl, so it's 80% H2O. Water is going to move. Solvent moves such that we equilibrate the concentration on both sides. So if we began this experiment with a water level of A and B that is approximately the same, we will have a net flow of water from A to B. So the level of water in A will go down, while the level of water in B will go up until I equilibrate the concentration on both sides. Osmotic pressure is defined as the pressure of an imaginary piston hovering over the surface of B that would be exerted to prevent any net flow from A to B. The more particles I put in B, the more the natural tendency is for osmosis to occur, the greater the pressure needs to be on this imaginary, hypothetical, square-headed piston. Osmotic pressure, therefore, will increase as I add particulate matter to chamber B relative to chamber A. Now let's talk about some mathematical functions. And I'm going to start with the most recent one, with osmotic pressure. Osmotic pressure is going to use the concentration unit of molarity. We're going to assume there's no change in temperature. By the way, if we looked at the gas law, PV equals nRT, and we solve for pressure, we get P equals N over V times RT. We call this pressure pi, and we use capital Pi. Moles per unit volume is molarity. And there is a factor called the Van't Hoff factor in case I have an ionic compound. So if I have glucose, I is 1. If I have NaCl, I have an idealized value of I equals 2. Now, when I can actually make this so concentrated that as they dissociate, they reassociate. So these are usually pretty dilute solutions. Around 0.01 molar is a very common concentration that we see with these colligative properties. But in doing calculations, you always use the idealized I equals 2 because it breaks up into 2 ions. Calcium nitrate is a very common ionic solid that's used to salt roads during inclement weather, this would break up into 3 ions, and it's also very cheap. So we don't use NaCl to salt roads. We usually use calcium nitrate because it's cheap, and you get 1.5 times the effect for a similar concentration of ions. So here's the equation for osmotic pressure. Let's talk about changing the freezing point, changing the boiling point. The depression of the freezing point, since of course water freezes at 0 Celsius, is minus I. Now we use molality, or M, times Kf. Kf will be a constant that is based upon the solvent. So Kf for water is 1.86 degrees Celsius per molal. If you use a different solvent, like an alcohol, obviously Kf will be different. This will be given to you in a problem. Delta Tb plus I m Kb. Again, Kb will be a constant for a given solvent. With water, it's 0.52 degrees Celsius per molal. These formulas may or may not be given to you. The constants most certainly would. Finally, if I want to know how much the vapor pressure is going to be lowered, P is equal to the mole fraction of the solvent times the pressure of the pure solvent. This is better known as Raoult's law. So now we're set up to solve any type of colligative property problem conceptually, but also mathematically. So in the next video that we produce, we're going to look at lots of applications of colligative property chemistry.